Hey, what's up guys? It's Dr. D-Flo and I'm here next to another large 3D printer, the OrangeStorm Giga by Elegoo. Don't let the quirky name fool you. The advertised capabilities of this printer are seriously impressive. It boasts a huge 800 by 800 millimeter build surface, as well as 1000 millimeters in Z-axis travel. Now, it's not often that I delve into product reviews, as my passion usually steers me towards DIY projects. However, the Giga's retail price of $2,500 caught my attention. At this price point, it promises to be either an incredible bargain or frankly a total letdown. I figured either way, this would be something that you'd be interested to know more about. For this review, we'll start with the assembly process. This will give us a chance to explore both the innovative and odd design choices Elegoo made. During the assembly, we will dive into the advantages and disadvantages of using a filament extruder for such a large volume, and what this means for this printer's applications. Finally, we will print a range of different objects, including tall ones, to check for any instabilities that may occur at the top end of the Z-axis travel. And with that, let's get started.
Dr. D-Flo.
When you order a printer this large, you have to be ready for the hassle of freight shipping. It's similar to ordering a refrigerator or washing machine, but there is no option to pay extra to get it delivered into the house. I was out of town when it arrived, but my strong wife was able to wrestle the two 150-pound boxes inside with a friend. Breaking into the boxes, I was impressed with how well the components were packaged. Each assembly was encased in thick polyethylene foam. Elegoo clearly understands that having to return a damaged printer is going to be a headache for everyone involved. However, their 14-day return window is narrow, so make sure you assemble the printer as soon as it arrives to check for damage. The printer is composed of four main assemblies: the base, left vertical guides, the right vertical guides, and the gantry. As you can see, the frame is mostly composed of 30 by 30 millimeter aluminum extrusion. Underneath the base, there are at least 6 extrusions supporting the build plates, which are attached through spring-loaded fasteners. Before printing, I will have to level each of the build plates manually, but we will discuss this and why the print surface is composed of 4 modular build plates later. I have to admit that I'm surprised by how rigid the frame appears. I was concerned that constructing a printer of this size with sufficient stiffness at this low of a price point was simply impossible. And while this frame may still not be rigid enough to support the high accelerations and print speeds advertised, at least it doesn't feel flimsy. After I had all the parts laid out, I did notice that one of the corner brackets was bent out of shape. This is where the cross member attaches to the top of the frame, and I was able to bend it back close enough that it didn't affect the squareness. We'll cover the assembly process step by step, but I must say this was the fastest journey from unboxing to printing that I've experienced. I have dealt with plug-and-play desktop printers that require more setup than this. In just 2 hours, I assembled the printer with the 90-odd fasteners, leveled the bed, and started the first print. That's including the time taken to reposition my cameras. I was thoroughly impressed by how easily it came together. To start the assembly, you have to join the left and right Z-axes with the base. This is accomplished with M6 bolts that run through the bottom of the Z-axis extrusions. They tighten into the base. Small corner brackets help to keep these assemblies upright, but they are quite small and you would expect some diagonal bracing for a printer this large. This is one of the reasons why many are concerned with this printer's ability to produce tall parts without significant ghosting, which occurs when the printer's vibrations show up in the extrusion lines. Don't worry, I will print a tall object later on and we will see if the lack of bracing affects the print as the gantry climbs higher. While the frame could use more support, the linear motion setup of the Z-axis is quite beefy. Each side features 2 25mm linear rods and 2 16mm lead screws. If the printer were to lose power, there is no concern for the gantry to lose its Z position. But what is a little disappointing is the small NEMA 17 motor that drives both of the lead screws. Just don't expect this printer to move quickly in the Z without stalling. Fortunately, this is not a requirement for planar 3D printing. Next, the Z actuators were braced at the top with more 30 by 30 extrusion on the front and back. Again, you can imagine why this is likely not enough support for this tall of a printer, but it wouldn't be too difficult to pick up some more extrusion to increase its rigidity. At this point, I was able to drop in the gantry, which felt right in place as it was keyed for the plates that were attached to the lead screw nuts. Let's quickly talk about the linear motion setup of the gantry. Both Y-axes are driven synchronously by a single NEMA 23 motor which is connected to pulleys on either side through a long rod. 10mm wide belts are wrapped around the pulleys, which are easy to tighten through knobs at the far end. As the belts are rotated, they move HGR15 carriages. The carriages are spanned by a 30x30 extrusion, which combined with another linear rail and a NEMA 17 motor make up the X-axis. This setup is perfectly adequate for driving the print head, but there is plenty of space to upgrade to larger motors in the future. Returning to the assembly, it should come as no surprise that I dislike running wire through drag chains and properly terminating my wires. It is very tedious, and I just went through the whole process for my upcoming video on setting up my new pellet extruder, so definitely get subscribed for that. Thankfully, wiring this printer was surprisingly straightforward. The wires were already pre-routed within the drag chains, eliminating a lot of the hassle. The main task was to install the brackets for the Z-axis drag chains. Once that was done, connecting the wires to the designated ports on the base was all that remained. It was as simple as that. Next we have the extruder, which was the biggest question mark for me. There is no information on Elegoo's website or Kickstarter campaign about the maximum flow rate for the stock extruder. How can you market this large of a printer without reporting the value that will most affect the print time? Once I got a hold of the Giga's slicer profile, I was able to find a max volumetric flow rate of 30mm cubed per second. To put this number into perspective, let's say we wanted to print a PLA cube that filled the entire build volume with 20% infill. It would take nearly 50 days to finish the print. If you wanted a solid cube, then be prepared to wait 250 days. By the time you finish your first print, the return window will have already closed. I kid slightly, but I really want to emphasize that if you want to print large models, then they need to be thin and hollow. This printer is going to be best suited for aesthetic rather than structural parts. Another disappointing aspect of the extruder is its reliance on proprietary nozzles. Their length places them between that of volcano and supervolcano nozzles, making third-party options incompatible. Additionally, Elegoo has not yet released hardened or CHT nozzle variants. This limitation means you'll be unable to print with composite filaments, which often contain abrasives. If you're interested in seeing an upgrade to a more capable extruder, please let me know in the comments. The printer ships with 0.4, 0.6, 0.8, and 1mm nozzles. However, for a printer of this scale, even a 1mm exit diameter feels somewhat limiting. With a 1.75mm feedstock, the nozzle has to be smaller than the incoming filament, so if I do upgrade the extruder, it may make sense to opt for one that supports the larger 3mm filament standard to unlock larger nozzles. Looking around the rest of the print head, we see an inductive probe for bed mesh leveling and 2 capable blower fans. I know that some of you are already starting to type in the comment section about the absence of a much faster surface scanner for mesh leveling, such as the Beacon, and yes, I agree. A printer this large would benefit greatly from a faster bed leveling option. While small for this application, the extruder was very easy to install. 2 bolts on the front and 2 on the back. A 4-pin cable provides the power and CAN data. The final 2 components awaiting assembly are the spool holder and the display. The Giga is equipped with a standard holder suited for 1 kilogram spools that will sit on top of the printer, alongside a guide bearing designed for larger spools positioned near but not on the printer. Both the spool holder and guide bearing are integrated with a filament runout sensor, which is crucial for pausing the printer when filament levels are low. Given the likelihood of requiring multiple 1 kilogram spools to complete a print on this machine, this system needs to be reliable. And yes, it successfully paused my first print upon running out of filament. However, the significant distance between the sensor and the tool head caused the filament to pile up behind the extruder. When the Giga senses that it's out of filament, it homes to the back right corner. As the print head got closer, the tangled filament knocked off the lever arm on the X-axis limit switch, causing a layer shift. This was after about 40 hours of printing, which was frustrating. But there are 2 solutions to this problem. The first is to use a reverse Bowden tube to guide the filament. Not sure why this wasn't included in the box. And the second is to use a larger spool. My friends over at IC3D sent over 2 of their massive 10 kilogram PETG spools. We will play around with these during a later print to make sure that the extruder has enough force to unspool this large of a spool. But first, let's finish up the assembly with the display. This 7-inch touchscreen is awesome. It slips over the top support, but can be removed to bring it lower to the bed during calibration. Although the screen features a custom Elegoo interface, the Giga operates on Clipper firmware. By connecting to the printer over Wi-Fi, you gain access to the standard fluid interface. It is strange, however, that there are connections on the bottom right of the printer. The USB port is in the perfect place for me to kick it. And the emergency stop button is recessed, making it not only difficult to press quickly due to its location, but you have to press it right in the middle, which may be hard to do if you're in a panic. Finally, the last mechanical assembly item is to tighten up all the bolts. Before plugging the printer in, you have to make sure that all 5 power supplies, yes, you heard me right, there are 5 power supplies in this printer, and they all need to be set to the correct voltage. The printer will consume close to 1500 watts, so make sure your outlet is rated for at least 15 amps. After the printer turns on, it will perform an initial homing routine. Once it finds its position, you need to probe the bed to determine if you need to manually level it through adjusting the spring-loaded fasteners, shown during the unboxing. It's best practice to probe the bed when it's hot to account for the thermal expansion of the build plate. I've set up a timer to see how long it takes for the bed to reach its maximum temperature of 90 C. While we wait, let's talk about why the build surface is divided up into 4 sections. This design choice appears to be driven by cost, allowing Elegoo to utilize their existing stock of heaters, plates, and build surfaces, components likely shared with their Neptune 4 Max printer line. When I built my large format 3D printer, I opted for a continuous bed instead of a modular one. My 1000 by 1200 millimeter Keenover heater cost $900. So I'm all for this cost saving measure, and while I initially had concerns about the potential seams between the 4 PEI sheets, with careful alignment, the transition between sheets are so minimal, they're hardly noticeable. So that took 13 minutes for the bed to reach 90 C. A common theme, which started with the extruder, is that everything is going to be slow, from the heating of the bed to the printing, and the bed probing is likely to be slow as well, so let's get started on that. As you can see, we're not looking too bad. The highest point is positive 0.21 and the lowest is negative 0.33. That is a max deviation of 0.54 millimeters. Take a look at the height map on the fluid interface. Not bad for out of the box. Let's see how close we can get the bed level with the manual procedure. First, we swap out the PEI build surfaces on the front half with these new sheets that have cutouts to provide access to the spring-loaded fasteners. After it probes the front, the display shows how far each point is from zero. One rotation clockwise will drop the point by 0.7 millimeters, while counterclockwise raises it by the same amount. You can reprobe a point after making an adjustment to see how far off you are. This process is repeated for the back build plates. Once finished, we can reprobe the bed to see if we eliminated all the peaks and valleys. Now our highest point is positive 0.24 and the lowest point is negative 0.09. That is a max deviation of 0.33 millimeters, or close to a 40% improvement before manual adjustment. Before we start our first print, let's quickly talk about the max speed and accelerations of the print head. The configuration file has the velocity set to 500 millimeters per second and the acceleration at 5K for the X and Y. However, Elegoo advertises a max print speed of 300 millimeters per second, but this number is always followed parenthetically by a 150 millimeters per second recommended or default speed. All these different numbers are odd, and I'm curious if the print speed is limited by the frame or the extrusion rate, which we already know to be pretty low. I devised a quick test to see how the printer performs at 150, 300, and 500 millimeters per second at the bottom and top of the Z travel. The acceleration was kept constant at 5K. I uploaded a G-code file that simulated printing a sparse infill in each of the 4 corners of the build volume as well as the center. I saw very little vibration as the extruder moved back and forth near the build plate at all speeds. This indicates that the base is rigid. But after climbing up to just short of the maximum travel and repeating the same routine, there was significant vibration in the top of the printer, even at 150 millimeters per second. This vibration was confined to the upper section of the frame, leaving the bottom stable. In practical terms, this means that while the printed part remains stationary, the print head vibrates noticeably. This discrepancy can lead to ghosting and layer shifts in the final print, a less than ideal outcome, but perhaps an expected compromise for a printer at this price level. We need to start printing to determine if this is a deal breaker, and we'll kick off our first print with a large-scale version of MacGyver's Articulating Dragon out of the supplied Elegoo's PLA Plus filament. This should be the ideal model to demonstrate the printer's capabilities in capturing intricate details. Plus, its relatively short height means we won't need to be overly concerned about the rigidity in the Z-axis during the print. The printer is equipped with a 0.6mm nozzle and is set to print at 200 millimeters per second with a layer height of 0.24 millimeters. All other settings were left to default on the provided slicer profile. The estimated time and filament to be consumed was 46 hours and 2.5 kilograms respectively. Overall, I'm very happy with the quality. There's only one noticeable flaw, that being the layer shift that occurred when changing the filament, as mentioned earlier. Although the slicer estimated a completion time of just under 2 days, or 46 hours, the actual print time extended to 63 hours, nearly 3 days. This equates to approximately a 37% increase in print time, a discrepancy I attribute to the notably slow travel speeds between print moves. A hidden setting in Elegoo's slicer profile has the travel limited to 300 millimeters per second, likely due to vibrations. However, for such a short print, you should be able to get away with 500 millimeters per second without artifacts creeping in. While I had to be patient, this print was worth the wait. There is an indescribable quality about the sheer size of this print that takes me back to the excitement of my first 3D printer. Let me know in the comments below if you notice other issues with this model. I'll admit my printing typically leans towards structural models where surface finish is less of a priority, but let's print something tall with my new 10 kilogram spools. I do need to make a large enough spool holder, which of course we printed on the Giga. For my next print, I'm going to try and tackle one of the 950 millimeter tall helical blades needed for my DIY vertical wind turbine. Even a small version of this would be difficult to print due to the narrow cross-sectional area that's attached to the build plate. For this reason, I added some custom support structures just to make sure it doesn't tip over. Because this part will be outside in the sun and rain, I'm going to print it out of IC3D's PETG filament. This color is blue raz, which should reflect the sunlight nicely while still blending in with the sky. I'm still using the 0.6mm nozzle and 0.24mm layer height. The infill is set to 25% with 5 perimeters and 5 top and bottom shells. I opted for a small brim to help with the bed adhesion. I originally had the speed set to 200 millimeters per second, but this was too quick, and the extruded PETG preferred to stick to the nozzle and clump up. This issue was resolved by decreasing the print speed to 125 millimeters per second and increasing the extrusion temperature to 255 C. I should have performed some calibration prints prior for this new filament, but I had a busy week and didn't want the Giga to sit idle until this weekend because this print was going to take 3 days and 7 hours. I adjusted the speed, temperature, and extrusion multiplier during the print, so definitely don't judge the first 100 millimeters or so of height. Wow, I can't believe this print didn't fall over. While the brim started to come unadhered, it didn't give up. Now before I get too nitpicky, the most important question for any 3D print, regardless of print quality, is, will this serve the desired purpose? And the answer for this part is a resounding yes. This won't have any issues functioning as a turbine blade. I'm going to finish that sustainable energy project over the summer, so follow me on Instagram if you want to stay plugged in on that. But what most of you are wondering is, how do the vibrations of the printer affect the print quality? Well, there's definitely significant ghosting. This artifact first shows up where the printer deaccelerates to go around the side of the blade at around 340 millimeters above the build plate. It becomes worse about halfway up, or around 510 millimeters, where it starts to occur in the middle of the part. Remember, the 125 millimeter per second print speed is under the recommended 150 millimeters per second, but this thin blade wasn't doing the printer any favors as it vibrates easily with any sudden movement in the frame. So I believe that I confirmed what many of us suspected. The somewhat flimsy frame of this printer will affect its ability to produce fine surface finishes for tall parts, especially at high print speeds. However, this likely won't affect the geometric accuracy of your parts unless you're looking for tight fit-ups. Before I get to my conclusions on this printer, I do want to quickly show you the Airless basketball that I printed from 95A TPU. This printer had no issues processing this often troublesome material. Make sure that you keep in mind that you'll be limited to PLA, PETG, and TPU as long as this printer remains open. Also, with this large of a bed, you can pack it full of parts, small or large, to make sure the printer is always running while you sleep or do other tasks. So here's my conclusion after printing for 2 weeks straight on the Giga. This printer is a cheap luxury. It's undeniable that the price per square footage, or in this case, the cubed footage, is unmatched. It would take the print volumes of 53 Ender 3s to equal 1 Giga. That is absolutely unheard of. But do you need a printer of this magnitude? I don't think so, which is why I've called it a luxury and not a necessity. Even for the enthusiast who has large objects to print, does it make sense to buy 1 Giga or several smaller printers and divide large models up? The latter option would be faster, as the Giga uses the same extruder as many of the desktop printers that Elegoo offers. So having multiple printers working simultaneously on sections of the same part would be significantly faster. My helical blade is the perfect example of something that could be printed in multiple parts and glued together. Of course, this printer's low cost for its size is both a pro and a con. Great for the wallet, but bad for rigidity. But those are my early thoughts on the Giga. I'm excited to use this printer for large, detailed objects that I'm not in a rush on. Let me know in the comments below what you think about this printer or what I should print next. And with that, I'll catch you in the next one.